All right, so we are ready to start again. So this is the page where we stopped last. So we went through the specs, so how we arrived at the specs and how do the specs make sense. Step by step we try to explain all of those. Now there is another set of desirables written over here, and they are most commonly going to be very important for wearable biomedical devices because they are power constrained, area constrained, they need to be low cost and so on. So making them low power and low area definitely is going to be very important, especially the particular application we are looking at where you are having multiple input channels. It may be 16, 32 or so many more. You need to have specific techniques to make sure that these each of these channels are occupying minimum amount of area. You may need to do some resource sharing, you may need to share, like just like you are sharing ADC, you may need to share the channel itself with the electrode. So some sort of resource sharing can be done. Apart from that, you can employ techniques for optimizing the feedback element, passive element, try to minimize the amount of capacitance you are going to use for the amplifiers and so on to reduce the overall footprint of the front end amplifier. So that is going to be very critical. And likewise, making it low power if it is a variable device, battery operated or operating based on harvested energy from different sources like body energy harvesting or solar energy harvesting and so on. There also we need to make sure that the power budget is limited. In general, for the biomedical device, front end happens to be the most power hungry block, and in the front end the first amplifier happens to be the most power hungry block, and making it low power and compact enough, that happens to be the most critical challenge. So making the front end amplifier low power is one of the most important tasks while designing multi-channel biopotential acquisition system. And the last point, of course, says that the design should be robust enough. It should be working for all the corner simulations. So generally, I guess since you have already been exposed to cadence simulations, you might have seen the corner simulation for any particular design where the same schematic is run for slow, fast, fast, slow, slow, slow and fast, fast corners. So they are just process corners capturing some effects of variations on the MOSFET transistors. And we need to make sure that under all these corners the design is working properly, it's meeting the desired specs. And apart from that, there are more rigorous simulations like Monte Carlo simulations that also need to be run, that we will discuss a little later. So this is about the high level functionality, the expected performance, behavior, and hence the specs of the front end design. Now gradually we need to start looking into the design itself, building it from scratch, transistor by transistor. And as I said, we are going to spend maximum amount of time on the front end amplifier because that happens to be the most crucial part, and then followed by that filter and some discussion on ADC. So before we start our discussion on the amplifier design, we need to revisit some of the important concepts which are going to be utilized all throughout the design. So here I have listed the same concepts, the same basic topics that I had emailed in a feedback form, and most of you recommended that we should have brief overview of all those topics. Basically, we just need to have a quick recap of CMOS analog electronics. First is MOSFET model, large signal, behavior, and small signal. Second is the application of MOSFET as a gain device. how do we use that MOSFET as an amplifier, what are the biasing consideration, what is the distinction between small signal, large signal, and so on. So that basically leads to the basic amplifier configuration. Single-ended, then differential, multi-stage, and cascade. We have to briefly discuss the frequency response and stability, because that's another important issue that comes into picture while analyzing the front-end amplifier design. We will be using stability analysis frequently while doing the feedback for achieving the gain of the amplifier. Also, for the biasing purpose, we need some common mode feedback circuitry. There also stability analysis will be important. Following that, we need to look into noise analysis. As we have mentioned in the very beginning, noise is a very critical parameter over here. So we need to look into the noise analysis of a multi-stage amplifier like an operational amplifier, and look into methods of how to optimize that. So these are the basic concepts I need to quickly go through so that we can apply these in the design. And while covering these examples, we will be gradually building on. We will be introducing those parts and subparts which will be finally utilized in the front-end design. So although it may look like some repetition for some of you who are already familiar with it, but a majority of you have recommended that these things should be covered. That's why I'm, through these basic constituent examples, I'm going through these. So when we talk about the MOSFET small signal model, so basically it arises from the fundamental current equation, the square law current equation that we have. So we can plot the ID versus VGS characteristics of the MOSFET. We can plot the ID versus VDS characteristics of the MOSFET, and from these two basically we can extract certain important parameters of the MOSFET that can be used in the small signal model and in analyzing the amplifier circuits using those small signal models. So what do we mean by large signal and small signal? So first of all, if we talk about the ID VGS curve, so how is it obtained? So for obtaining the ID VGS curve, we would say that okay, we have to sweep the DC voltage at the gate. So we have to apply a VGS and sweep it. In the simulations also, cadence design environment, you can set up this simulation, you can apply a DC voltage at the gate and sweep the parameter from 0 to maximum voltage and plot the current. You have to just observe this current flowing, and you can just connect it either directly to some larger potential, maybe VDD, or you can set it to VDD by 2. So you can keep it at 0.9 volt, and the VGS is varying from 0 to say 1 volt, where VT is say 0.3 volt. So these are the nominal values for say 180 nanometer technology. This is your VT. So below VT the current happens to be very small, so it will be close to 0, and on linear scale just after you cross VT you get a steep increase in current. The MOSFET is on, and as long as VD is greater than VG minus VT, the transistor is in saturation. So this is a large signal operation. We are just sweeping the gate voltage of the MOSFET, and we are getting an current at the drain. From here we can derive an important small signal parameter just by taking the slope of this curve at a particular VGS, and that gives us del ID by del VGS. We call this GM small signal transconductance. So, if I am at a particular VGS and I am changing the VGS by a small amount delta, how much my current is changing? That is determined by the small signal transconductance parameter GM, which is an important factor for the MOSFET small signal parameter. Now, on the other side, we have the ID VDS characteristics. How do we obtain the ID VDS? So, here we need to choose a VGS. So, we need to fix the VGS to a certain value. So, here we have fixed the VGS. So, this is VGS fixed, and make it greater than VT, so that you have it on, and then you apply a DC potential VDS. You can sweep it starting from 0 all the way, say, up to VDD. So, once again in cadence you can apply 2 voltage sources, fix one of them, another one VDS you can sweep, and you can measure the current which is flowing into the drain. So, that gives us the ID VDS characteristics. So, here once again we have clear demarcation between 2 regions of operation. One is the triode region of operation, where the VD is greater than less than VG minus VT, and in that region there is a strong dependence of drain current on the drain voltage. The current drops down almost linearly with VDS. Once the VDS crosses VGS minus VT, goes above, then the current happens to saturate, and the slope is much flatter. So, here once again this slope is determined by the channel length modulation factor lambda, and the output, the slope of this curve determines the small signal impedance looking into the drain. So, it basically tells us that if I am biasing, if I am fixing the VDS, changing it by a small amount delta VD, by how much amount my drain current is going to change. What is that small delta ID I am going to get for this small delta VDS? So, that means this is going to give me the small signal incremental resistance looking into the drain of the MOSFET. So, this is the large signal curve. I am increasing VDS all the way, I am getting the drain current. Now, at a particular VDS, if I say that I am biasing the MOSFET, that means I am choosing a particular VDS and a particular ID. That means I am choosing a biasing point. My MOSFET is nominally at this point, and then I am applying a small VDS fluctuation across the drain and source. Corresponding to that, I am trying to measure what is the small signal current getting injected into the drain. What is the change in the current? So, that change in the current delta I is the small signal current or the AC current that we are trying to measure. So, the small signal applied voltage delta VDS and the small signal change in current delta IDS. So, the ratio of delta VDS upon delta IDS will give us the small signal output impedance of the MOSFET looking into the drain. So, there are the 2 important parameters which we need for building the small signal model of the MOSFET, low frequency small signal model of the MOSFET. So, how do we capture those? So, the well known so the transconductance is captured as a voltage dependent current source, and the drain to source resistance RDS is captured as a parallel resistance connected between the drain and the source terminals. So, this is a small signal low frequency model. We have not yet included the effect of parasitic capacitances in the MOSFET. Before we do that, there are using this model we need to arrive at certain important parameters, certain important characteristics of the MOSFET when it is being operated as a small signal device. So, once again, if we are say talking about small signal amplification, we are trying to apply this MOSFET in magnifying analog signals. So, let us try to build a simplest amplifier with this MOSFET. So, you have RD, the MOSFET device. We first of all talk about the biasing point. So, you need to set a VG capital VG a DC voltage so that it is having an appropriate biasing point. Recall from the earlier plot that in order to have an appropriate GM, we need to choose the VGS. So we need to fix the VGS at a proper point so that if I change my VGs by a small amount across that point, I get a large change in ID. Then I will get a large signal current, sufficiently large output current flowing into the drain when I change my gate voltage by small amount. So when I say a signal current, that means a change in current. So we are talking about this application of MOSFET in building an amplifier. So the very first thing is we need to have an appropriate biasing point. So in this curve, as we mentioned, we need to choose a particular VG and a particular drain current value across which we want to vary the signal, across which we want to fluctuate the applied VG and hence get a small change in current. And if there is a small change in current, that can be converted into a change in voltage by applying a resistor over here. So whatever delta I we are producing, that will be getting multiplied by this RD and producing a delta V out or a small signal voltage. So this basically gives us an amplification between the applied input voltage and the output signal. So we are having the DC bias, and on top of that we are applying an input signal V in and getting a magnified signal at the output. So regarding the small signal operation, there are some important characteristics of the MOSFET to be noted. First thing is the small signal gain. So most of us are familiar with the small signal gain expression. So for a given input signal V in, we are having an small signal current given by GM times V in, and that gets multiplied by RD, gives us an overall output signal GM times V in times RD. Therefore, the overall gain for the simple common source is GM RD, the magnitude. Of course, as compared to the input signal, we know that the polarity is going to be opposite. So if the signal is going up, the drain current will increase. As a result, the voltage will go down. As a result, you are having a negative sign. You can also do the small signal analysis. You can apply an AC signal over here in the small signal model and put the source at ground and then put an RD over here, exact analysis, and then solve for the V out as a function of V in. That gives you the negative sign automatically. So we can of course resort to small signal analysis whenever we need to find out exact expression, we have any confusion, etc. But in most of the cases right now, I will skip the small signal analysis. Intuitively, I will just arrive at the final result for all these circuits we are going to discuss. Now, a couple of important parameters that we would like to see is the impedance looking into the drain of the MOSFET. So that is very well known. We have just discussed that if the gate of the MOSFET is biased at a DC point, what is the impedance looking into the drain? It is simply RO, the channel given by the channel length modulation. RO is equal to 1 upon lambda ID. So how to measure the output impedance of a given amplifier? That is the first step. So for measuring the output impedance of a given amplifier, the rule is that you set the AC signal at the input to 0 and then draw the equivalent AC circuit. Now AC circuit means all the DC point will be set to 0, because all the DC potentials, they are not having any AC current or AC signal. The DC voltages, they are not having any fluctuation. As a result, they will be grounded. So you are having an AC ground over here, you are having an AC ground at the gate, AC ground at the source, and then you have to find out the input output impedance looking into the drain of the MOSFET. So there, the total output impedance will be given by the test current IT, which flows into it when you apply a voltage VT. So this is the test voltage. So I can comfortably say that if I am having an AC voltage VT applied at the drain under this condition, VT upon RD is going to go up and VT upon RO is going to go down. So I can just visualize this MOSFET in terms of its small signal model. So this is the small signal model of the MOSFET that I will be assuming here. I can just visualize it that if I am applying a VT over here, the small signal resistance looking into the drain will be just given by RDS. VGS is 0, the VG is also ground, S is also ground, so you don't have the small signal current flowing, this is 0. Therefore, the MOSFET can be simply represented by RDS. So whenever we are talking about the impedance of the MOSFET looking into the drain such that the gate is at AC ground, gate is not having any AC signal, the impedance looking into the drain is simply RDS. And therefore, the total impedance looking into the output port will be RD parallel RDS. So this is a simple conclusion we can have here. Now, if I want to find out the impedance looking into the source of the MOSFET, so somebody has given me a circuit like this. The gate is at DC potential, drain is also at DC potential. So I put them at AC ground. I want to find out under this condition if I am applying a small signal AC at the small signal AC voltage at the source, what is the input signal current flowing into the source, and hence what is the input impedance. So how do we do that? Without even doing the small signal analysis, we can see that the gate voltage is at AC ground. We have not applied any AC signal or small signal over here, and therefore the VGS is simply minus VT, and as a result the drain to source current is going to be minus GM times VT, and hence it is going to be from source to drain. So GM times VT current flowing from source to drain, and hence the input impedance can be given as VT upon GM VT, therefore 1 upon GM. So impedance looking into small signal AC impedance looking into the source of the MOSFET with its gate at AC ground is given by 1 upon GM, and that is also going to be useful in repeatedly being used in many design scenarios. So these expressions should be handy, they are very common, and in order to proceed with analog design, these are some of the very fundamental relationships which have to be almost remember. If at any point, because these are very important issues, very important concepts, so at any point if you have questions, feel free to ask. I can take 1 or 2 questions in between if there are any issues in understanding this, because I understand that later you will be going back in December. We have to possibly upgrade this course and go into more details, and many of you suggested me over email that it will be good to give these details also. So definitely I will try to have a more detailed version apart from whatever I am covering here. I will try to have additional lectures uploaded where I will try to elaborate these topics a little bit more, so that students who are very fresh to these topics, who have not dealt with analog design extensively earlier, they can also be comfortable with it. So
are you able to hear me, sir?
Yes.
So these basic electronics was covered 5 years back in IIT Bombay. That time I was a student there. So that videos are still available on basic electronics. So people can watch those videos. Those are also under university and freely available.
Okay, yeah, that will be helpful. But this is, I guess, not going to be a complete overlap. So as I am going forward, most of the modules that are going to cover here, they are going to be a part of whatever designs we will be doing. So hopefully it's not really going to be complete overlap with those modules, and of course catering everybody's requirement is
Hello sir.
Yeah,
actually such kind of videos are available online, but it would be better for sir if you kindly provide this.
Sorry
sir, these kind of videos are available online, everyone knows that, but still it would be better for the students or for us if you kindly provide this.
Yeah, so we'll try to produce those materials online. So here whatever we are discussing, apart from that, additional material will be uploaded. We'll try to create the appropriate videos for that as well. Okay, so now these are the 2 important results that we need to remember. Apart from that, some other very important results that are frequently used in amplifier designs. Now, if we are supposed to find out output impedance for this device, so you are having some DC bias point for this amplifier, some gate voltage is applied, and then you are having a test signal applied at the drain, and you are trying to find out the small signal current IT flowing into the drain. Earlier case, when we put the source to ground, the output impedance was simply given by RO. In this case, I have just made one change. I have inserted this RS. Now, what is the impedance looking into the drain of the MOSFET? Anybody can tell? RO plus RS? Anybody else? Yes. Yes, so approximately GM R naught RS. And without even doing the small signal analysis, how can we say that? So, if we, in the small signal model, if I am not including the RO of the MOSFET, so in many cases when we do the small signal analysis, people may ignore RO of the MOSFET. For example, in the common source example that I just took, for example here, I just wrote the gain GM RD, and here the assumption is that the RO of the MOSFET is much larger, the RO of the MOSFET is much larger than RD. So, the small signal impedance here should be RO parallel RD, but if RO is much larger than RD, then they can ignore this. So, that is the assumption, but in many cases if we ignore RO, we can end up in trouble. For example, here if I ignore RO, the impedance looking into the drain that we would get is going to be completely incorrect. Let us, without going into the small signal derivation, we can just look into this circuit and find out how we are going to get the overall impedance. So, rather than injecting a voltage, I can just rather inject a test current. So, both the ways we can evaluate the output impedance. So, suppose I am taking out the RO, I am drawing the RO separately, and I am having a test current injected. So, both test current and test voltage can be used to find out the impedance. So, now if I inject a test current into this branch, the same test current should come out of this, whatever is going into this branch, the same test current should come out of this. So, the source voltage over here should be Vs should be equal to IT times Rs, and now the gate voltage is having only DC. So, it is basically AC ground. So, I can, in the AC model, I can just set it to 0. I have an AC ground over here. So, the VGS just becomes minus IT times Rs. Therefore, the small signal current that is flowing, that is going to have plus IT times Rs direction upward, GM IT times Rs. So, this drain current plus GM IT times Rs is going to flow into this RO, because remember, this is an ideal current source, it is not going to change its value. So, whatever small signal current is coming out of this dependent source, that entire value will flow through RO. Therefore, the potential drop across RO, like we can call it VRO, that is going to be IT Rs times RO, right. And then I can add, if I have to find out what is Vt, so Vt is going to be equal to VRO plus VRS, the voltage drop across Rs plus voltage drop across RO. So, I have IT Rs RO plus IT Rs. So, approximately I can say it is approximately equal to, sorry, I missed the factor GM. So, you have the GM factor coming here. So, GM RO times Rs plus Rs times IT is your Vt, and therefore, Vt upon It gives you the impedance looking into the drain. So, that is approximately equal to Rs plus GM RO times Rs, and if I know that GMRO is going to be generally significantly greater than 1. This is the intrinsic gain of the MOSFET, right? So intrinsic gain of the MOSFET means if you are having a ideal current source connected over here, you are having ideal bias current connected over here, and you are looking at the gain V in to V out. The ideal current is having infinite impedance, only the MOSFET's impedance RO comes into picture, therefore the overall gain is going to be GMRO. So that is the intrinsic gain. So GMRO times RS. So if you are having a impedance RS connected in the source, the impedance looking into the drain of the MOSFET gets boosted by GMRO times RS. So that is another fundamental relationship that can be remembered, and once again it is very important in design of high gain amplifiers. For example, if we have a structure like this, what is the impedance looking into the drain of this structure? Suppose these two are bias, VG1, VG2, DC bias. What is the impedance looking into the drain of these two MOSFETs? Anybody? GM R naught square. So here you have R naught. So basically GM R naught of this MOSFET multiplied by R naught of this MOSFET. So you are getting a GM R naught square. So you are able to boost the impedance up, right? Now how do we make use of this active impedance or impedance boosting? So let us see. So far we have used, we just talked about the resistive load MOSFET, and the gain is around GMRD. If we ignore RO, if we want to improve the gain of this MOSFET, what are the techniques available to us? Either increase GM or increase RD. Now, apart from, so what are the trade-offs? So if I increase RD, how far I can go, and what is the bottleneck? So if I go on increasing RD, the output DC point is going to go down further and further for a given VGS. A particular VGS is supplying current dependent upon the current equation VGS minus VT square, and as you are going to increase the RD, the VD will go down further and further, and finally the drain voltage will drop below VG minus VT. Transistor will enter into triode region. So there is a fight between gain and swing. So that is another very important parameter for designing amplifiers. We need to consider the gain as well as the allowed output swing. So if I am trying to have larger gain just by increasing RD for a given input DC bias at the gate, the drain voltage will go down. As a result, my allowed swing for the signal will be diminished. So for example, if my output characteristics is over here and my VG is biased at a particular DC point, and if I am going on reducing my RD, so in that case my we are trying to for a particular VG, if we are going to increase the RD, our DC bias point at the drain drops down further and further, and the transistor is going to enter into the triode region, and your gain is going to finally drop, and you are not going to get any amplification. Apart from that, there is a condition of symmetric swing. I will not go into all those details because I guess I have to limit these discussions. An alternate way to do is to increase GM, and to increase GM we have a couple of options. GM depends upon ID, W by L, mu n COX. So once again, either I can increase ID or I can increase W by L. So if I increase ID, the same thing is going to happen. Once again, the DC point over here is going to go down, transistor is going to enter into triode region. If I increase W by L, once again, there are other issues that can come into picture. If I am increasing W by L, there are parasitic capacitances associated with the MOSFET, the CGS and the CGD, which we have not discussed yet. So the parasitic capacitances can once again start making your amplifier slower, the frequency response will be degraded. We will discuss the frequency response very briefly once we finish the discussion on biasing and active load. So both the ways we are having stringent bottleneck with the gain. So another alternative is to use active load. So you can use PMOS load, for example. Now here I can bias the gate of the PMOS at a particular voltage VGP, and under that condition we know what is the impedance looking into the drain of the PMOSFET, that is just going to be ROP. Impedance looking into the drain of the PMOSFET with gate at a fixed potential, that is just going to be ROP. And therefore I can just imagine this circuit as a MOSFET with an ROP connected. The good point over here is that the DC point at the drain under this condition is not linearly dependent upon ROP. For the RD, the DC point over here was linearly coming down as I was increasing the RD. But for a PMOSFET, the drain to source relationship with respect to the bias current is not really linear, or with respect to RO is not really linear. For the same bias current, I can increase the RO of this MOSFET without linearly degrading or lowering this drain voltage. So that basically helps us achieve much higher gain while maintaining an appropriate DC point. So that is the main advantage of having an active load. So it can give you larger gain without degrading the DC bias point. Now if we know the technique, for example, to boost the gain over here further. So in this condition, what is the so we have seen just now that if we, for example, cascade two such PMOS transistor at the load, VGP1, VGP2, under that condition, and taking the output at this point, suppose. So this is again a common source amplifier. We are applying an input over here. At the drain we have connected two PMOSFET transistors. Gates are biased at two different DC potentials. And now can we expect any improvement in gain over here? So here my impedance looking upward is GM RO square. That's what we mentioned earlier. So if you are cascading two PMOS transistor or NMOS transistor like this with gate voltages at DC bias, impedance looking into the drain will be of the order GM RO square. Impedance looking into the drain of the lower one is only RO. So I can call it ROP, and this is RON. So here if I am talking about an input signal, AC signal, I am only drawing the AC part. I am not really depicting the DC bias point over here. So I am talking about the AC signal applied at the gate. Corresponding to that, you are going to have a small signal current flowing. That small signal current is going to get divided into the RON and GM ROP square. So basically you are having a parallel combination. So if I just draw this MOSFET with the signal, you are having a parallel combination of RON and GM ROP square upward. So the drain current of this MOSFET, the small signal drain current of this MOSFET is going to flow through these two resistances or parallel combination of these two resistances, and hence the RON is going to dominate because this is a smaller one, and hence we are just going to get the intrinsic gain or close to the intrinsic gain GM times RON, no such advantage. So the technique to really exploit this effect of impedance boosting is to cascade another transistor stack, another NMOS transistor on the top of the main amplifying device. So that is called the cascode device or cascode amplifier. So now my input is applied at the gate. This is VGN, a DC bias, fixed DC bias. VGP1 and another one, VGP2, and then I am taking the output over here. Now here, if I just look at this MOSFET, what is it facing? It is facing some impedance upward. So still I am looking at a common source amplifier. Easiest way to visualize it, input signal is at the gate, source is grounded. So this is a common source device. It is having some load connected. So I just need to model what is the load upward. So here we have a different scenario. We are looking into the source of the N MOSFET. We just saw that if we have a N MOSFET with drain at AC ground and we are looking into the source, what is the impedance of that? 1 by GM. But in this case, can we say the same? So let us see what happens if you are having an N MOSFET with some arbitrary load RD connected, gate at AC ground, and then we are applying a, say, test current IT. We have to account for the RO as well. Now, under this condition, we need to find out what is the VT developed over here. Now, once again, in this case, rather it would be more convenient if I just start with VT, because we are at the source. So suppose I am applying an AC signal VT. So in this, once again, I have VGS is equal to minus VT, and hence I am going to get a small signal current GM VGS flowing from source to drain upward. So GM times VT, and this current is going to get divided between RD and RO. So what is the current factor which is going into RD? So I can just write GM times VT times RO upon RO plus RD is the current going into RD, right? So whatever current is coming out into RD, that must be coming out of this source, because this is once again a two-terminal device. This black box is a two-terminal device. Whatever current is being supplied by VT should exit into RD. Therefore, this is the same current which is coming from VT. So I can just write down my IT as this current, and therefore VT upon IT gives me the input impedance, which is GM RO plus RD upon GM RO. What is this? 1 upon GM plus RD upon GM RO. So this is the earlier expression 1 upon GM that we got if we did not have any RD. So in that case, the impedance looking into the source of the MOSFET is just 1 upon GM. Whereas now once we have an RD connected, then it is resulting in another additional term RD upon GM RO. If the term RD is much smaller than RO. So RO in a MOSFET, say 180 nanometer technology, if you are using nominal bias current, RO can be still few tens of kilo ohm to 100 kilo ohm. RD on the other hand, if you are biasing a common source amplifier, still would be few kilo ohm at the max. So passive resistor RD may be significantly lower than RO, so you can ignore this. But suppose now once again I replace RD by a MOSFET. So in this case we have a similar condition. So we are looking into the source of this MOSFET, say call it M1, M2, M3 and M4. I am looking into the source of this MOSFET M2. It has some impedance connected into the drain. So looking into the source of M2, I have some impedance connected into the drain. What is that impedance? Once again, same thing, whatever we discussed just now. GM, yes, GM3, RO3, RO4, right? Intrinsic gain of this device GM3, RO3 times RO4, RO4 of the upper MOSFET. So this is the impedance which the M2 is seeing upward. M2 is seeing upward, and therefore, if I just look at the order, if I say that all the GMs and RO are same, so M2 is just looking at GM RO square. So in that case, what is the impedance looking into the source of M2? Gm Ro square upon Gm Ro plus 1 upon Gm, right? So it is approximately Ro plus 1 upon Gm, which is approximately, which is going to be much larger. In general, Ro is much larger or 1 upon Gm is much larger? Ro happens to be much larger. 1 upon Gm, if you are having enough bias current, it can be around 10 to the power of minus 3, 10 to the power of minus 4. So Gm will, 1 upon Gm will be few kilo ohms. Ro few tens at least, it can go up to few hundreds of kilo ohm easily. So we can ignore this. So approximately it is Ro. So now impedance looking into the source of this M2 is not 1 upon Gm, but it is approximately Ro. So now if I want to find out the gain of this circuit, that how much output voltage is produced if I am having an input signal applied to the gate, how do I do that? So first of all, I will have to look at M1. So I know now what is the impedance connected from the drain of M1. So if this is M1, what is the impedance connected, small signal impedance connected between drain of M1 and the VDD, which is basically an AC ground for small signal analysis. That is Ro. I have just found out that the impedance looking upward is just Ro, and then you are applying an input signal V in. In this case, what is the small signal gain from input to output? So it has its own small signal impedance Ro, both connected between the drain and AC ground. The first one between the drain and the VDD, which is AC ground, another one between drain and AC ground. So overall you have Ro by 2, and as a result the overall gain from V in to V out will be Gm Ro by 2. But we are not interested in the gain over here, right? This is not my output node. My output node is over here. So how do I find out the gain in this case now? So for that we need to see what is the current going up. If I know the current going up into the source of M2, we know that the same current is going to exit into the drain of M2 also. And if I just multiply that current by the total impedance looking upward, I get the voltage, right? So again, I will just find out, because of an applied voltage over here, what is the current going into the source of M2, small signal current going into the source of M2. The same current will exit into the drain of M2 as well, and I can multiply that with the impedance looking into the drain of M2, right? Any problem in this discussion? Okay, so once again we can look at the current division. You are having an Ro of the M1, Ro looking upward. So we know that Gm Ro by Gm V in is getting divided between the Ro of M1 and Ro looking upward, because impedance looking upward is also Ro. So we get a Gm V in by 2 as the current going upward. And then we have the impedance looking into the drain of M3 given by Gm Ro square. Therefore, what we can say is the total gain is Gm Ro square by 2. So we are getting square of the intrinsic gain by 2. This is the basic principle behind cascade amplifier, which can give us large gain corresponding to two active stages or two intrinsic gain stages. So in order to obtain a Gm Ro gain, you need an ideal current source load connected to the single common source amplifiers, and the cascade amplifier gives us square of that gain just in a single stage. So this is one technique of achieving larger gain in a single stage. What is the other other possible methods for enhancing the gain? Rather than going for single stage, we could have simply cascaded multiple stages of amplifiers, right? So we can take two common source amplifier, cascade them. We can get, say, GMRO from one stage, GMRO from other stage, GMRO square. So what is the advantage or disadvantage of the two cases? So suppose I have an active load, Vin applied over here, this is VGP. So this can give us, first I can just cascade two such stages, output of one going to the next stage. So first one is going to give me GMRO by 2, another one GMRO by 2, so overall GMRO by 2 square. So I can get large gain by just cascading two stages. What are the pros and cons of these two different approaches? So if I look at the first case where I am relying on relatively higher impedance at the output, right? So what are the purpose of cascading these two NMOS and PMOS transistors? To get a very high impedance over here. So at the output node we are having a very high impedance. Impedance looking upward into the PMOS, GMRO square. Impedance looking into the drain of the NMOS, GMRO square. As a result, the RC time constant at the output node is going to be much larger. So we said that MOSFETs are going to have their own parasitic capacitances, and at each node of the circuit we can find out the total parasitic capacitance from that node to ground. So suppose there is an overall parasitic capacitance from this node to ground, and as a result the pole, the RC time constant corresponding to this node is going to be determined by the total parasitic capacitance here, which is based on the dimension of these transistors and the overall impedance over here. Since the impedance over here is so large, the RC time constant over here is going to be very high, and as a result the pole, that is 1 upon RC, is going to be very low, and hence the speed of this circuit is going to be much slower. Whereas in this case the overall impedance is just RO by 2, and as a result the RC time constant is going to be smaller, poles higher, and hence the speed higher. So this circuit, if you are just cascading two circuits together, you are achieving higher speed because you are having relatively lower impedances at this point. But what is the cost? You are having two stages, you are burning more power. Now we will see the use of these two techniques. We will be using multi-stage amplifiers, specifically the differential and the two-stage differential amplifier and folded cascode amplifier, and seeing what are the pros and cons for these two topologies while designing the front-end amplifier for the chosen application. Now this is about the single-ended version. Of course we can translate the same discussion to the fully differential case. So in the very beginning we said that whatever processing we are doing with these analog circuits, they are going to be in fully differential mode, because differential amplifiers provide immunity to common mode interference, common mode noise from different sources. So translation from single-ended to differential is straightforward. Many of us have seen at least the basic analysis that is done for the differential half circuit and the common mode half circuit. So let us start moving towards the differential mode operation and try to arrive at the multi-stage amplifier, two-stage amplifier in case of the non-cascoded load, and try to see how we can apply that to build a relatively large gain amplifier, and then what are the issues associated with that particular amplifier while doing appropriate biasing, while sizing the amplifier and choosing the bias currents, etc., and make it operate as a robust large gain amplifier. So once again I will start. Feel free to interrupt if there is any issue, anything not clear, or if anything is too redundant. Because I understand here 25% of the people, in the feedback they said they had no issues, most of the things were okay, but 75% they had issues, and as a result, if I cater only to the 25% who are already working in analog side and disappoint rest of the 75% who are more towards digital, and they will be not so comfortable with whatever we are doing over here. So that's why I am trying to spend some more time to bring everybody on the same page. Otherwise, I may be losing 75% of the audience, and that's going to be disappointing for all. And in such a gathering, of course, it is very challenging to satisfy both the ends. Having in-depth and detailed discussion, research-oriented discussion on the design part, and at the same time, meet the expectation of people who are just starting to enter into analog phase. So we have to have a balance point. So here, the differential amplifier shown over here, the simplest way to analyze this, we say that any particular signal can be broken down. If you are having any arbitrary signal V1 and V2, you can break it down into the differential signal Vd V1 minus V2 by 2, Vd plus and Vd minus V2 minus V1 by 2. Likewise, the common mode signal can be just represented by V1 plus V2 by 2. So I can represent any arbitrary signal V1 and V2 as a combination of the differential signal and the common mode signal at these two gates. And for the differential signal, this node happens to be an AC ground, and I can just break this circuit into two half circuit, treating this as an AC ground, and then my whole problem is just like a common source amplifier. So all the topologies that we discussed just now can be treated in a similar fashion. For the differential case, I can just break down the half circuit. For the half circuit, again it translates to the same topology as a common source amplifier with different loading conditions. Now, we have discussed advantage of active load, that an active load, it is having the advantage of high gain. It is also having the advantage of higher swing. So it is able to achieve high gain while retaining sufficient swing. But also there is another disadvantage of the active load as well. It is difficult to address in the single-ended version. Therefore, I did not really point it out over there. But in the differential version, it is easier to address, much more convenient to address that issue. And that is to do with the DC bias point at the output node. So if I now draw the active load, the PMOS load, suppose both of them are VGP, and you are having a so here in the first case, if I am biasing the differential amplifier with a base current IB, I know IB by 2 is flowing in both of the branches, and therefore VDD minus ID by 2 times RD is the DC bias at this point. So I am sure about more or less I am sure about my output DC points. Of course, RD is not going to be a very precisely controlled value. RD can vary by maybe 10%, 20% on an integrated circuit. If you choose the RD value of 10 kilo ohm, it can turn out to be 12 kilo ohm or 8 kilo ohm. It is feasible, but still to a good extent you have a control. You know what is the expected value of the drain if you know the RD and the chosen value of bias current for this differential amplifier. Therefore, I know the DC operating point at the output. And remember, in order to bias a circuit, in order to bias the amplifier in a high gain region, we need to ascertain the DC bias point at the output as well as the input. So once again, recalling the both the characteristics, ID, VDS, in order to have sufficient gain, we need to make sure that the VD is VG as well as VD we need to make sure that the VD is midway so that when you are changing the Vg and the signal is swinging for no value of Vg, the signal enters into the triode region. So, and likewise we also need to ensure that you are having appropriate biasing condition for the Vg, so that it does not, the extremes, the upper and the lower extremes for which the transistor will be coming out of the saturation region. So, I need to set the DC bias point at the input as well as at the output, and in this circuit it is being achieved. But here we cannot say precisely what is going to be the DC bias point at the output. We can always solve for the DC bias point numerically if I have the lambda values given for this transistor and these two transistors, because if I assume that these are perfectly matched transistors, my two transistors are syncing IB by 2, IB by 2, I can use the lambda p and lambda n, equate the current in this 2 and this 2 and find out the exact value of Vd assuming saturation region condition. That is possible, but in general these parameters lambda, they are very much process dependent, they will fluctuate widely from device to device on the same chip, and as a result these are not very well controlled voltages. These DC voltages are not well controlled unless we use some other technique to stabilize them. So that is that requires some additional technique called common mode feedback to make sure that these DC operating points are fixed and stable. So let us see how do we apply common mode feedback to achieve a stable DC point for active load differential amplifier. As I have said, any point not clear, please feel free to interrupt. Now, in order to take the common mode signal, just like we define the common mode input signal as V1 plus V2 by 2, we can define the common mode output signal as the average of these two signals. So, if you are applying an input signal, a differential input signal, one of them like we expect the output signal to be showing the same trend, and once again we can define the average of these two signals V out 1 plus V out 2 by 2 as the VOCM. And in order to get such a average, we can use different mechanisms. One of the simplest one is just use high value resistors R, and the output over here gives us the VOCM. What is the problem with this? What can be the prospective problem of using this R? Why do we want it to be high? Why do we need this R to be high? What is the, now if I want to analyze the small signal model for this circuit. So, once again suppose I want to find out the exact expression for the gain. What is the small signal gain of this differential amplifier? Differential gain, I am not talking about common mode. No change. What will be the small signal AC equivalent? So, here I have an AC ground over here, you are having an AC ground here, AC ground here. Input signal is applied here and here. This is still an AC ground, no problem, I can treat this as an AC ground. But what about the differential half circuit? Is this an AC ground? If I am having a differential signal applied V plus, V minus, this is going to be an AC ground, right? Because these two signals are in opposite direction, this plus this by 2 is, this is always going to be stable at the same point. So, this is going to be an AC ground for a differential signal, right? And therefore, what happens to the overall resistance over here? This R is going to come in parallel with RO of N and RO of P. if I do not have this R, if I do not have this R, in that case my half circuit will contain only this portion, right. This is an AC ground and my half circuit is just the NMOS with a PMOS active load, and my gain is GM RO by 2. But now if I have this R in the half circuit, this point is an AC ground, and therefore my half circuit is going to have PMOS, NMOS and this R connected between this drain and AC ground. Therefore, the overall impedance over here is going to be R parallel ROP parallel RON, and if R is lower than ROP and RON, in that case once again it can reduce the gain. So, I need to make R much greater than ROP and RON. ROP and RON can be several hundreds of ohm. That means R needs to be mega ohm in order to avoid its effect on gain, right. And in general, achieving very large resistance value, implementing large resistance values using passive resistors happens to be challenging because it requires larger area. Using active devices, using transistors, we can implement large resistances. We will see some good examples as we go deeper into the design of the front end amplifier. But there can be other methods also. We will see without using resistors also, using active circuits also, we can extract the common mode signal. Now here we have the common mode signal extracted. Suppose we are managing to get a very large R value, and hence the output common mode voltage is available to us. Now next is how to establish a common mode feedback. So I can use an error amplifier, which is like an amplifier with a differential amplifier with a very large gain. Suppose we have an ideal differential amplifier with a very large gain available to us. So now I can connect the common mode output voltage to the positive terminal. The negative terminal is connected to a reference common mode voltage, VCM ref. This is the common mode voltage to which I want to set the actual common mode voltage. Now under this condition, if the VOCM goes higher than the desired value, the output will be going high. Now check a condition when it will be happening. So assume under certain condition the threshold voltage of the PMOS reduces in magnitude because of some reason, because of temperature or because of some time dependent parameters. The mod VT P reduces. As a result, it starts supplying more current, and as a result the output voltages over here, the DC level is shifting up, which is undesirable because it is drifting away from the required common mode voltage. Now I can see the voltage of this error amplifier increasing. I can feed it back to the PMOS gate voltage, and as a result it will automatically bring this gate voltage to a higher value and try to adjust it so that the VOCM and VCM ref are once again set to very close values. So that is a function of error amplifier. It will always try to force the VOCM close to the VCM ref by the use of this negative feedback. Once again, the moment we see that the threshold voltage of this PMOS is reducing, mod VTP is reducing because of some effects, it will start supplying more currents to the output nodes, both of them. The common mode DC level at the drain will start increasing. As a result, VOCM will start increasing with respect to VCM ref. That will increase the output of this error amplifier, make it more and more higher, and that should again go to the gate of the PMOS and reduce the current back to the original value. So it is having a negative feedback and is trying to control the output DC point. So this is the common technique we will be that is generally used for stabilizing or biasing the differential amplifier with active load. Now some other issues related to the same scheme. If we if we talk about, say, the feedback, wherever we are employing a closed loop feedback in a system, we need to look into the stability of the system. So if you're having a feed forward path gain AS and a feedback path beta S, and you are having a negative feedback, so in general, for such a feedback system, we need to make sure that the phase margin for the loop gain A beta is being met. And what do we mean by that? Once again, if we just revisit the concepts of loop stability, if I want to make sure that this feedback loop is going to be stable, we must make sure that the frequency at which the mod A beta, which is a function of frequency, is the frequency at which the mod A beta is becoming 1, the phase is less, the phase is not crossing 180 degree. If it happens, then this denominator will shoot up. So if I just plot this condition, so in general, I guess overall transfer function can be of the form, say, 1 plus S upon P1, 1 plus S upon P2, and so on. So in general, the S domain transfer function can have multiple poles. So the P1, P2, P3 denote the pole of the system, and I'm assuming that I'm ignoring zeros. I'm assuming that there is no zero in the denominator. So given an open loop system, suppose it is having an arbitrary form, it is having say n number of poles. So the Bode plot, that is the magnitude of the gain as a function of frequency, we know what is the curve looks like. So after the first pole, say P1, it is the smallest pole. After that, we have a minus 20 dB per decade drop. After P2, we have a minus 40 dB per decade drop, and after P3, finally minus 60 dB per decade drop. And what happens to the phase? So what happens to the phase plot? So if I am starting from 0 degree, each pole introduces a 90 degree shift. So let me plot it over the same scales. So assume it will be difficult. Let me change. If I am plotting the phase plot likewise, so each pole introduces 90 degree phase shift. So if I am starting with, say, 0 phase shift at P1, it crosses 40 minus shift of 45 degree, and far away from P1 it approaches 90 degree. At P2 another step of 90 degree, at P3 another step of 90 degree. So at each pole it basically gets another shift of 90 degree. So in order to make sure that the point at which it is crossing 0 dB on the gain axis, that the magnitude is dropping below 1 along the x-axis, the phase is sufficiently higher than 180 degree. It has not crossed 180 degree. We need to have a certain margin with respect to 180 degree, and that is denoted as the phase margin. In order to make sure that happens, we need to ensure a condition such that the gain curve is crossing the 0 dB point at 20 dB per decade slope only. That basically ensures that the phase margin is going to be 45 degree. And how does that happen? Let us see. Phase margin of 45 degree is highly desirable because it leads to minimal overshooting and highly damped response for the oscillations. So, if I am trying to make sure that my grain, my second pole is located beyond the point where the gain is crossing 0 dB. So, after P1 the gain starts dropping by minus 20 dB per decade, and before it reaches P2 I need to make sure that it has crossed 0 dB. So, in that case I know what is going to be the phase plot. For P1 I am going to have a drop of around 90 degree, and then before it reaches P2 my gain has already dropped. At P2 exactly I get an exact phase drop of another 45 degree, and far away from P2 it reaches once again minus 180 degree. So, at P2 exactly we have minus 90, another minus 45, so minus 135 degree. So, at the second pole the overall phase shift of the loop is exactly minus 135 degree, and as a result I can say that I am 45 degree higher than the 180 degree mark, the danger mark, and hence I have a 45 degree phase margin. So, that is the sufficient condition generally employed. We must make sure that the point by which the point till which the gain is dropping to 0 dB, my second pole is not encountered. So, if I make sure that the second pole is at the 0 dB crossing point or higher than that, then I am safe. Then I have a phase margin of 45 degree and higher. So, that is the general stability criteria applied while ensuring the stability of multi-stage amplifier, say two-stage op-amp or even folded cascode op-amp and so on. So, we will be using this basic concepts to verify the stability of the amplifier we will be designing. Any questions regarding this? I guess these things must be.
So, we talk about differential amplifier. We require that both the common emitter stages making the differential amplifier should be identical in all respects, like beta, like VB, everything. How shall we decide that which terminal will be non-inverting and which will be inverting? Because both transistors are identically matched in all respects. Same resistance we are using in the collector.
Yes, so here we are talking about fully differential circuits.
Yes, fully differential.
So, if you are having a differential amplifier with diode connected load, so there you have a polarity at the output. Here it is fully differential. Any part can be inverting, any part can be non-inverting. Means any input port can be inverting and non. So
it is
positive and negative. So the definition of positive and negative is arbitrary.
So how we come to know about which will be positive or which will be negative?
No, positive and negative is just a definition. So you're talking about inverting and non-inverting. That means with respect to the input, you have to see which output you're talking about.
That is the practical approach.
Yeah, means I was confused with the polarity. Polarity, there is no fixed definition of polarity there. The term that you used was once again your the term that you asked for was.
Sir, I mean to say that
inverting and non-inverting.
Inverting and non-inverting.
Yeah, so for inverting and non-inverting, you just have to look at the relative locations from which input to which output.
Okay, thank you, sir.
I guess I'm.
Yeah. Sir, one question. Sir, we have cascaded the devices and there is a VSB appearing for M2. So we have completely neglected body effect in the entire derivation.
Body effect we have ignored because we are already running short of time, and I'm just trying to recap these things quickly so that we can proceed with the
But in
actual design.
biomedical application, will it affect, because it will reduce the impedance?
Generally, of course, if you are having amplifier topologies where you are having multiple stacks of amplifier, multiple transistors in the stack, like folded cascode amplifier, there your transistors which are higher up in the stack, away from the sources, VDD and ground, they will be having body effects. But in general, our target happens to be achieving very high gain and then use those amplifiers in feedback. So as long as we are having sufficiently large open loop gain, we need not really worry about nonlinearity issues coming out because of body effect. Other issues like dependence of impedance, etc. Yes, it may depend, but we are not really looking at very precise gain obtainable just by open loop. It is just a requirement for get a sufficiently large gain. I don't really need to be precise about calculation.
Sir, good afternoon, sir. This is when we are multiplying two stages. In multi-stage amplifier, when we are having two stages, then are we considering loading effect again in the calculation part? Loading effect. Because we have taken A1 into A2, that is A square gain.
Yes.
So are we considering loading effect while designing? Because here we are not taking.
There is loading effect is inbuilt there. So we are not. So whenever we consider GMRO square, so we are already incorporating the RO of the lower transistor and then looking upward. So there is no separate need of incorporating any loading effect. Yes. Any other question?
Sir, in your discussion, you told that cascode amplifier has less bandwidth and two-stage amplifiers more bandwidth, whereas two-stage amplifier have more capacitances. Whereas cascode amplifier, that Miller capacitance is killed by the cascoded stage.
Impedance is much higher. So at the
not in terms of impedance, bandwidth, frequency response.
Yeah, frequency response depends upon the pole at the output, right? So RC time constant.
Yeah.
So at the output node, if you look at the total capacitance, capacitance will not be very different from the two cases, because both of them are having the drain of the MOSFET, NMOS, PMOS. Resistance in the two cases are very different. Cascode stage is GMRO square, here it is RO. So you are getting a factor of GMRO which can be 50 to 100. As a result, the poles will be different by that factor.
But in two-stage amplifier, Miller capacitor plays a role. Cascode amplifier, that Miller capacitor is killed by a cascode stage itself. That's why bandwidth is increased in cascode amplifier compared to two-stage amplifier.
Once again, please.
So in cascode amplifier, so we'll have the Miller capacitance. That capacitance is killed by the killed by the cascoded stage. Whereas two-stage amplifier, you'll have the Miller capacitance. That won't be ignored.
No,
Miller capacitance will decide the bandwidth.
No, so so Miller capacitance will come if I did not really talk about the driving stage, that you are having some impedance over here and you are having a source over here. I just talked about the output pole. So how fast is the output node? So in general, if the driving source over here is having high impedance, then it can dominate. But if the driving source is not having much impedance, then the main pole will be at this node. And in case of the cascodes, this particular node is having much larger impedance. So as a result, if I just look at the RC equivalent, the very high R value over here and similar C value is definitely going to have a much larger RC time constant as compared to even if you include the Miller capacitance at this node. So you are going to get a GMRO term for this guy, and the capacitance is CGD. So for example, if I just compare, that depends upon the driver stage impedance. If the driver stage impedance is too high, then yes, it can affect. But if the output pole is the dominant one, then of course that is the major So we will see in our particular application, since the electrode is going to have a very high capacitive value, the capacitor basically dominates, and with respect to the overall pole coming, the output node dominates as compared to the input node. So the main concern is the output node and not really the input side.